We just solved an example using Navier-Stokes equation for a two-dimensional motion in rectangular coordinates xy and determined the value of pressure. We try to do a similar exercise now, but this time by using cylindrical polar coordinates. And therefore, let us see the given problem that has been given to us. The pressure field that is given to us is UR is equal to theta, that is the radial component of the velocity is theta, whereas U theta, the radial component in the theta direction, is given by K by R, where K is some constant and R is of course the radius. So therefore, it is obvious that U of theta is inversely proportional to R. As the R will increase, the U theta will be reducing, but when R is decreasing, U theta is increasing. It is required that we calculate the pressure as a function of R and theta. So this is also a case of two-dimensional motion of only R and theta, and the third component in the cylindrical polar coordinates R theta z. Z component is not there, it's missing. As before, we look at the continuity equation and we observe that the continuity equation is identically satisfied for the given field of velocity in which UR is theta is 0 and U theta is K over R. If you look at this type of motion, then you can see the flow field looks like in this manner, that, as I also remarked earlier, as we move away from origin, that is, as R increases, U theta reduces. So the motion is reducing away as we for large R, and when we come closer to 0, then it is increasing steeply, and in fact, so it forms a line vortex. This we call this as line vortex. There is a swirl in the motion that is taking place. Now, looking at the equations, at the theta component of the Navier-Stokes equation, when we write it in component form, the terms are evident and the partial derivative contributions coming out of the given field, and the given field is only one, U theta equal to K over R, where K is a constant, R is the radius, and of course UR is 0. So these are the values that we obtain, and the equation reduces to, it does not give us anything really, all the things are 0 from there. So we then come to theta component, and the only term that is non-zero is this. So we will have minus 1 over R dp by d theta is equal to 0, and from that, if I multiply throughout by R, I will obtain dp by d theta equal to 0. And in a similar fashion, I try to find out the R component, and from R component, I obtain this equation. So, as was the case in the rectangular coordinate example, we are left with two equations for P, and we can find out the value of P if we integrate it with respect to theta, and we can find out the value of P again if we integrate it with respect to R. The second derivatives, of course, are 0. So when we integrate it for theta, I will have P of R is equal to 0, but plus some constant of integration, and because this is a motion in two variables, therefore, as a rule of differentiation and integration, we write down the constant of integration as G of R, because there is a possibility that it depends on R. If it comes to an absolute constant, well, that will make our life easier. And similarly from R, we obtain dp by dr is equal to g of r, and that equals to this quantity. You can see PR is equal to GR, and all I have to do is take its partial derivative. That will be G prime R, that is derivative of, but dP by dr in R terms is given to us, and from that I obtain the value as equal to rho into k square over R cube. And you can see that it is not difficult to find out the value of G from here. And G therefore, after integrating, turns out to be this, where C is a absolute constant this time. And when I substitute it into the value of P, then P of R theta is equal to minus 1 by 2 rho k square over R square plus C, where C is absolute constant. And as a remark, as we said earlier, C does not really contribute much. The contribution again is coming from this quantity, and that also when the gradient develops and the gradient changes, when we differentiate it with respect to R, we will have the motion taking place. The absolute value of P does not really make any contribution, and you can see the Bernoulli's equation also being identically satisfied for these conditions. At the two-dimensional line vortex, in the end, is a simple approximation of tornado. This example, if we try to find a similarity with a real life motion, then you may have come across, then during the summer weather, there are a lot of tornadoes that take place, particularly in the areas that are either in the desert or close to the desert, and this is a very common phenomena. Those who live in those areas, they may have come across, and this very much looks like a vortex. And so this kind of motion occurs, and in fact in many countries, including United States of America, the tornadoes plays havoc with the area in which they take place if they are very stormy. And in that case, the houses are blown up, the cars are gone. So there are a lot of loss of man and material from time to time whenever such incidences occur. And it's so important to consider this type of flow and try to find the remedial methods, how we can take care of this motion from taking place.